A ball is thrown vertically upward from the top of a 30-meter high building with an initial velocity of 5 meters per second. At the same instant, another ball is thrown upward from the ground with an initial velocity of 20 meters per second. Determine the height from the ground and the time at which they pass. So let's look at a drawing of this situation, then we can understand it maybe a bit better. So over here in the black ink, I've drawn the building. It's 30 meters high, and the path of the blue ball, or ball A. It's thrown up with an initial velocity of 5 meters per second, and at some point it will turn around, it will come down under the influence of gravity. And at ground level, at 0, we throw ball B up, and it'll go up, and it'll come down again under the influence of gravity. And at some point here, I've drawn a little red line there, these two balls will cross each other, and it would be at a certain time. Remember, we start the stopwatch when the balls are thrown up, and it would be at a certain height above the ground, which I've indicated here by h. So the question is, at what height and time do they pass? We've got two unknowns. So if you think about this, when they pass, their height above the ground would be the same per definition. So we can take the position equation for both of these and we can equate them because they should give us the same position above the ground. So for ball A, I've written that in blue. We can say S is S0 plus V0t plus a half AT squared, and we can say at the instant where they pass, that's going to be the same as the position of ball B. S0 plus V0t plus half AT squared. That's our equation of motion. Now it's important that we measure the position from the same reference line. So we measure the position, in this case, from the ground up. That is why if you look at the second line, S0 for ball A is 30 because it's thrown from the top of the building, while S0 for ball B is 0 because it's thrown from the ground. And we reference our motion, our position from the ground. So for ball A, 30 plus 5t, that is 5, that is our V0, minus a half, 9.81. 9.81, gravitational acceleration. Why a minus? Because we take gravitational acceleration as negative downwards. And in both cases, the balls have been thrown upwards, so the velocity is positive, initial velocity. T squared is equal to 0, that's the initial position of ball B, plus 20t, 20, that is the initial velocity of ball B going 20 meters per second upwards, minus a half, 9.81, again, gravitational acceleration, multiplied by t squared. In the next line, I've just multiplied everything out, simplified, and you get 15t is 30, and you solve for t, and you see t is 2 seconds. So at time is equal to 2 seconds, the ball A and ball B will be at the exact same height from the ground. That's the time when they pass. Now when we have the time when they pass, we can plug that into our equation for position, and we can know at which height they also pass. So you can take any one of the two position equations, either for ball A or for ball B, and just remember that ball A is measured from the top of the building and ball B is measured from the ground. We want to know the height, so we want to measure it from the ground. So I'm just going to plug it directly into the equation for position for ball B. And at t is 2 seconds, we can say the position of ball B is S0, so that's 0, plus V0t, V0 is 20, t we've just found is 2 seconds, minus a half, gravitational acceleration, multiplied by t squared. And then if we calculate that, we get 20.38 meters. So after 2 seconds, these two balls will be at 20.38 meters, and they will be at exactly the same height, and they will pass each other. Let's look at another example. The acceleration of a particle along a straight line is defined by a is equal to 2t minus 9 meters per second. So here you can see that acceleration is not constant. Acceleration here is a function of time, where t is in seconds. At time equals 0, s, position, is 1 meter and velocity is 10 meters per second. Now the question is, when t is 9 seconds, determine the particle's position, the total distance traveled, and the velocity. We cannot directly use our equations of motion because our acceleration is not constant. So we need to work from first principles and integrate with a variable acceleration to get our answer. So let's look at question number 1, the particle's position. So we know that A is dv dt. So dv is A dt. We integrate on both sides. If we integrate dv between v0 and v, we get v minus v0. And on the right hand side, we integrate A dt from 0 to t, but this time we cannot take A out because A is not constant. So there I've substituted in the equation for A. A is 2t minus 9. We need to integrate that. If we integrate that, we get v is equal to, and I've taken the v0 over to the other side. You get integrating 2t, you get t squared. Integrating minus 9, you get minus 9t. So that is now an equation for the velocity. Now we need to integrate that again to get our position. So we know v is ds dt, so ds is v dt. We integrate ds, that gives us s minus s0. And on the right hand side, we're integrating v dt. Now we know what is v because we've just found it from acceleration, and we substitute it in there and we integrate, straightforward integration, and now we can substitute in our boundary values. We know that v at 9 seconds is 10 meters per second. We know our time is 9 seconds. We substitute that into there and we get a position of minus 30.5 meters. That's the answer to question number 1. Question number 2 is the total distance traveled. So now we need to take into account the path the particle takes in this time of 9 seconds. So we need to know where does the particle stop and turn around, change direction. We need to add all those distances together. So we need to take the velocity equation and set it equal to 0, solve it, and see where we have points of 0 velocity, because that's where the particle turns around. So after integrating the equation for acceleration that we were given, a is 2t minus 9, we found that velocity as a function of time is 10 plus t squared minus 9t. By setting the velocity equal to 0, we find that the particle stops at 2 points. The first one is t1 is 1.298 seconds and t2 is 7.701 seconds. And these points are important to consider when we determine the total distance traveled. So, the total distance traveled is the distance traveled from time 0 to time 1.298, that's when it turns around. Then again from 1.298 seconds to the second point where the particle stops, 7.701 seconds, and then from 7.701 seconds to 9 seconds. So we break this integral up into 3 integrals to consider each section of motion between the points where the particle stops. So we once again integrate velocity to get our position. And if you remember this table, this is where we can see that we need to integrate velocity to get to our position. So we have an equation for velocity. We found that in our previous question 1. And so we can substitute that in for v. And we can integrate that, straightforward integration, just takes a bit of time. And we substitute in our boundary conditions and we get 56 meters. So the total distance traveled is 56 meters. Note that this is not the displacement. The displacement is the final position minus the initial position. So the displacement does not take into account the path that it has traveled. This is the total distance that it has traveled. Then the third question is, what is the velocity at t is 9 seconds? So just at t is 9 seconds, what is the velocity? So this does not take into account the path that the particle has traveled or anything like that. So we can just integrate our acceleration to get velocity. We have done that already. And we found that v is 10 plus t squared minus 9t. And we can substitute 9 for time. And we get that the velocity at t is 9 seconds is 10 meters per second.